Hello, everybody. Welcome to another video. Today we have Chapter 3, Atomic Structure. And we're going to be talking about atoms and how they're made and what they're made of and stuff. And we're going to go into a lot more different topics. Kind of a lot of review from Honors Chem once again here. We have things like electron configurations, protons, neutrons, electrons, ions, isotopes, mass spectroscopy, photoelectron spectroscopy, and a little bit about light. So we have a lot to get through today. We're going to go over each topic pretty quickly. Some of it you should be very familiar with. Some of it you might need a little bit refresher on, but hopefully the chapters, we're not quite to the hardest stuff yet. Okay. So our topics are atomic theory, average atomic mass, electron configurations, spectrometry, and light. Right. So starting with the atomic theory, very similar to like the cell theory you talk about in bio, the atomic theory just tells you what atoms are, what they're made of, what's our current going theory about what atoms are. So this kind of lists out the rules. Stuff like this, listing the rules of the atomic theory specifically, is not something I want you to focus on when you study. This just kind of so you know. Like there's never going to be a problem on the AP exam, like what's the third rule of the atomic theory? But still information we should know to help give ourselves a reference going forward. Number one, each element is made up of tiny particles called atoms. Number two, the atoms of a given element are identical. The atoms of different elements are different in some fundamental way. Right? A gold atom is the same as any other gold atom, for the most part. But every gold atom is different from every single uranium atom. Number three says chemical compounds are formed when atoms of different compounds or elements combine with each other. A given compound always has the same relative number of types of atoms. Compounds are combinations of one or more types of atoms together. And then lastly, number four, chemical reactions involve reorganization of the atoms. The atoms themselves are not changed in a chemical reaction. Okay. The structure of the atom, hopefully we know pretty well, but we're going to go over it again. The atom contains these three main subatomic particles. We have electrons. They're found outside of the nucleus in orbitals. They are negatively charged, and their mass is really, really small. It's basically zero. It's actually like 1,000 times smaller than a proton or a neutron. The reason for that is that electrons are actually fundamental particles, meaning they can't be split down any further. They're not made of anything else. They are as small, as far as we know, as a particle can be, right? It has no parts that make it up, which is not this case with the proton and neutron, actually. Protons and neutrons are both found in the nucleus. Protons have a positive charge that is equal but opposite to the charge of an electron. So they kind of cancel each other out. If you have two protons and two electrons, it's really like having no charge. They cancel each other out. They're the same charge but opposite to each other. The neutrons are found in the nucleus, also with no charge at all, and they have the same mass essentially as a proton. So when we're looking at the atom, all the mass comes from the protons and the neutrons found in the nucleus, meaning all the mass of the atom comes from the nucleus. The electrons are around the outside in orbitals. They're so small they hardly even contribute to the mass at all, but they do contribute charge. Okay, here's our picture. A very simplified picture, not super accurate, but we have in the middle protons, in blue the neutrons with no symbol on them, meaning neutral. And then around the nucleus in different orbitals are the electrons. Now the nucleus is extremely, extremely small. That picture we just looked at is nowhere near to scale. We'll look at one that's slightly more to scale, but it'd be impossible for me to show you an actual 2-scale picture and you actually still be able to see the nucleus. It's that small. Okay? It's also extremely dense. All of the mass, all the protons and neutrons are in the nucleus. So it accounts for almost all of the atom's mass, like 99.9%. When we calculate the mass of an atom, we ignore the electrons completely and just add protons and neutrons together. So here's a slightly better picture of kind of what an atom would look like. So we have an atom, it says a diameter of about a billionth of an inch or a few billionths of a centimeter, so incredibly small scale. In the very middle, you have the nucleus. The nucleus is about 100,000 times smaller than that. So that means if this whole atom is a billionth of an inch, this would be 1/100,000th times smaller than that, right? So this is not to scale. This nucleus here is still way too big. You would have to have the tiniest, tiny little dot in the middle that we couldn't even show you because 1 pixel would be too big. Okay, so the nucleus is incredibly small, meaning all of this empty space is what the atom really is. The atom is just mostly empty space. The electrons are somewhere in this clouded area called the electron cloud. They're also drawn way too big in this picture, of course. They would be even smaller than the nucleus. Okay. And they're drawn a little bit smaller, but they'd be even smaller than that. And they just kind of orbit around in crazy, weird patterns we're going to learn about inside of this clouded area. So an atom, all the mass is concentrated into this tiny, tiny little bit in the middle. And all these atoms are or all these electrons are super small negative charges that kind of whirl around unpredictably in this area. Yep. So it says the electrons are 1,000 times smaller than even the nucleus, which I said the nucleus was too small to even fit to scale on this picture. So you can just the scale is kind of weird. And all stuff is made of these atoms. And I don't feel that empty, right? I don't have all that empty space. Because these things get packed in so close together, they give us the illusion of solid material that has no holes in it, but everything is mostly empty space. Okay, a couple vocab words we have to go over. Atomic number is just the number of protons in an atom. It also determines its identity. If we take a look at the periodic table, okay, the number at the top is the atomic number. It tells you how many protons it has, and you'll notice every single atom has just a different number of protons. The number of protons determines what its identity is. Okay? The number of protons is also called the atomic number. Anything with 12 protons is a carbon atom, regardless of anything else. It doesn't matter how many neutrons, electrons, or anything else it has. If it has 12 protons, it is a carbon atom. Atomic mass, as we said, is the mass of the nucleus. Electrons are too small to be significant. The unit for atomic mass is special. It's called atomic mass units. If we tried to measure it in like grams or something, we'd have to use incredibly small numbers. So we kind of made up our own units called atomic mass units. The proton and neutron each have a mass of about 1 AMU each. So a proton weighs 1 AMU, so does a neutron, which makes calculating mass really easy. If you add together the number of protons and neutrons, that's the mass of a single atom in atomic mass units. Another word here is isotopes. Isotopes are atoms with the same number of protons but different number of neutrons. So just to talk about it, we're going to come back to that slide in a second. Here are two isotopes of sodium, and I just want to kind of compare and contrast between the two to see the differences between them. Both these things are called sodium. That's all you'd have to call them. They both have 11 protons, therefore they have to be sodium. Okay. They have 11 electrons as well. So in this cloudy area, they have 11 electrons whirling around there, 11 protons in the middle, meaning those charges cancel each other out. It has no charge because it has 11 positives and 11 negatives. The only thing different between these two pictures is the number of neutrons. The one on the left has 12, the one on the right has 13. Okay, that's going to make their masses different. If we look down here at this symbol, right, this nuclide symbol is what this is called. The number down here is the number of protons, 11. The number at the top is the mass, which is 23 because here's 11 plus 12. This one's 24 because you have 11 plus 13. There's no really any difference between these. If you looked at a sample of sodium, there'd be trillions and trillions of atoms. Some of them would be this one, some of them would be this one. Sometimes there are differences between isotopes, and that really comes down to how stable the nucleus is. Okay, nucleus math and chemistry is really complicated actually. So like why would one of these be more common than the other? It just has to come down to the forces of the nucleus here. Does this prefer to have 12 neutrons or does it prefer to have 13? One of these might be more stable than another, meaning one of them might be radioactive. Radioactive things decay over time because their nucleus is unstable. That's really the only difference between the two. They would do the exact same things. They would react with the exact same atoms and their compounds and stuff. It's just the stability of the nucleus is slightly different between them, meaning some of them are more common, some of them are less common. Okay, so they show almost identical chemical properties because the chemistry of the atom is due to its electrons. The number of electrons are staying the same in all those examples, so there's not really any differences. The number of protons aren't changing, so you still have sodium. Changing the number of neutrons can really only affect the stability of the nucleus, leading the atom to be radioactive or unstable. The number of neutrons usually don't alter other properties. There are some examples of ones that do with very, very small atoms sometimes. You might have heard of something called like heavy water. And heavy water is just made of all water molecules, or mostly water molecules, with heavy isotopes of hydrogen in the water molecules. And that just makes it slightly more dense because there's slightly more mass in it. So certain things that normally wouldn't float in water would float in heavy water. But like there's no chemical difference between the things. So some of the physical properties can change. In nature, most elements contain mixtures of isotopes. So, carbon, you would find carbon that weighs 12, carbon that weighs 13, carbon that weighs 14. There's not any difference between them except carbon 14 happens to not be very stable, so it's radioactive, meaning there's very, very little of it. Next vocab word is ions. An ion is an atom or group of atoms that have a net positive or negative charge. An electron, like we said, has a charge of 1 minus. Okay? Electrons are rearranged in chemical reactions. The first electrons to be lost are those furthest away from the nucleus, called the valence electrons. Protons will never be added or removed during a chemical reaction. Chemical reactions move electrons around, but the nucleus stays the same. A couple more vocab words. We have cation, which is a positive ion. A positive ion means you lost electrons. A common misconception is that it's positive, meaning you gained protons, but the nucleus never changes in a chemical reaction, so it's only electrons you can add or remove. So to make something positive, if you remove a negative charge, that's another way to make something positive. An anion is a negative ion. That means you have to have gained electrons to get more negative charges. The way I remember which one is which, anion is the easier one. That prefix a just means negative, right? Like asymmetric, right? Something like that. So a is just a prefix for negative, so I can remember anion's a negative charge. Cation, you can either remember that cats are super positive creatures, or that there's a letter T in the middle, which kind of looks like a positive sign. So either of those things would like help you remember that cations are the positive charges. All right, we're going to run through an example here of looking at atomic number, atomic mass, and charge, just to kind of see how they're all related to the number of protons, neutrons, and electrons you have. Okay. So here I have the example copied down on my paper. Look how prepared I am. So we're going to look at each of these and figure out how the pieces of information relate to each other. So atomic number, we learned, is essentially just the exact same thing as number of protons. So anytime you know the atomic number, you know the number of protons too. So I have 11 protons. My atomic number here is 11. I should have explained this before we started. This chart, basically you have 3 different atoms, and it kind of goes this way. You know the number, their atomic number, their protons, their number of neutrons, their mass, their number of electrons, and their charge. And with knowing only a couple pieces here, we should be able to fill in all the rest. So I should have explained that better. If you had me before, we've done tables like this a lot, so you probably knew what we're talking about. But if you didn't, you might be really confused. All right, so first, like I said, atomic number and protons are directly related. So if you know one, you easily know the other. The second thing that's related, atomic mass. Atomic mass is just protons and neutrons added together. Right? So it's your number of protons plus neutrons equals atomic mass. Meaning in this example, we know the mass is 14, and we know how many protons we have. Therefore, we can figure out we have 8 neutrons. 6 plus 8 gives you 14. The last thing we're able to discern from this is our charge. To find out charge, we have to compare protons with electrons. Okay. Protons and electrons compared to each other. And you just compare the number of each one. If you have more electrons, you have a negative charge. And in this case, since I have 2 more electrons, I'm going to say I have a 2 minus charge. My net charge here, when I add these two together, is minus 2. I have 2 additional electrons. Okay, and that's basically the relationships we use in this table. So if we go to the next one, I'd already filled in the atomic number here. So if I want to look at the atomic mass next, this time I know my number of protons and neutrons, so I just add those together. My mass is 25 AMUs. Right, I need to figure out my number of electrons. I know my charge, and I know my number of protons. I have a 1 plus charge, which means I have 1 more proton than I do electrons. Since I have 10 protons, or sorry, 11 protons, I have 10 electrons. That would give me that net charge of 1 positive. In this last example, I kind of started you off backwards. So kind of thinking over here, charge, you need to know about your protons and electrons. I don't have either of those yet, so I have to come back to that. Here in the middle, neutrons and atomic mass, I might be able to figure something out. Mass is protons and neutrons together. I have the mass, I have the neutrons, so I can guess at the protons being 15. 15 plus 16 gives you 31. I can also fill in, since I have 15 protons, my atomic number must be 15 as well. These two columns will always be the same. And now I need to get my electrons. So for electrons, I have a 3 minus charge, which means I have 3 more electrons than I do protons. 15 protons means 18 electrons. And that's how you can use protons, neutrons, electrons to figure out atomic number, atomic mass, and charge. Oops. All right, the average atomic mass is the weighted average of all the different isotopes of an element that occur in nature. So if we look at the periodic table tells us average atomic mass. It's actually the numbers on the bottom of the box. When we're talking about the mass of an individual atom, it always comes out to be a whole number, or very close to a whole number. That's because you just always have a whole number of protons and neutrons. You can never have half of a proton or half a neutron. But almost all these numbers on our periodic table are decimals. And that's because these aren't the mass of one atom. These numbers are the mass of the average atom, taking into consideration all the different types that exist. Okay, so like we said a moment ago, we said carbon. Let's zoom in here. Carbon has carbon 12, that weighs 12, carbon 13, and carbon 14. All three of those exist. Carbon 12 is by far the most common though. So when you take the weighted average, meaning the average weight of all the different types of carbon that exist in the universe, this is our number that we've calculated, 12.011. Most of them weigh exactly 12, but because a couple of them weigh 13 or 14, it actually changes the average to be just over 12. And you notice that's the case for like most atoms. Most of them have these decimals, right? If you go to the really large atoms, some of these don't, especially these in brackets. The ones in brackets aren't naturally occurring, and this is the only isotope we've able to make appear in a lab. So that's why you see them in brackets like this with only one number. This is the only type that we currently know to exist, right? Okay. We also care about molar mass. Last time we learned that molar mass is the number of grams per mole of a substance. And we actually said it was that exact same number. And that is true. This number tells you both things. It was intentionally designed to be both things. The number at the bottom tells you the mass of the average carbon atom or any other atom, and it also tells you the number of grams in 1 mole of that atom. So we very intentionally designed these units so it can tell us both pieces of information. Okay, so that can be a little bit confusing. This is simultaneously the weight of one atom and the weight of 6.022 times 10 to the 23rd atoms. Just because our units are different, we designed our units to work that way. All right. Average atomic masses unit is AMU, and molar masses is in grams per mole. Okay, so here we have some information about chlorine. It says determine the average atomic mass of chlorine using the information below. So all I have here is I have two isotopes, chlorine 35. If you see it written like this with a dash and a number, that's telling you its mass. It's a mass number. So this is chlorine that weighs 35 AMUs, and I have chlorine that weighs 37. They don't appear equally in nature. It looks like according to our percent abundance, chlorine 35 is more abundant. Chlorine 37 is a little bit more rare, but they still both appear pretty often. Okay, so if we go to this example, I've copied, again, these numbers here. We want to find what does the average chlorine atom weigh. Now, a common thing that happens here is you take a regular average, meaning, okay, well, one of them's 35, one of them's 37, so they must weigh 36 AMUs on average. which would make sense if they both appeared 50% of the time. But they don't. One of them is more common than the other. Therefore, we have to take a weighted average. So what you're going to do is you're just going to multiply across. You're going to do 35, multiply by its percentage, do 37, multiply by its percentage. Okay? There's a little bit of a problem that this is a percent. It's going to mess up our answer at the end, so we can change it to a proportion, meaning we can just move the decimal place over. Now you can choose to do that now before you multiply, or you could just divide your answer by 100 at the end. So like either way, you'll get the same answer. But so this, you're going to do 35 times 0.7576 or 75.76. Just remember to divide it by 100 later. And when I do this, 35 times 0.7576, I get a number, 26.516. The bottom one, I multiply 37 times 0.2424. Oops. 37 times 0.2424. And I get 8.9688. Some of you were asking me about rounding stuff earlier. This isn't my final answer, so I'm not really worried about rounding unless I have to. If I had a super long number with like 30 decimals, I'm going to round it. But in this case, I'm just going to keep it together. It'll make my final answer more accurate. I'll just round my final answer instead. So I'm just going to add these two things together now. What each of these numbers represent is each isotope's contribution to the overall average mass when you consider how rare it is or how common it is. So when you add these two numbers together, 35.48. Sure, I'll round it there because my answer here has 4 decimals. I'll just keep 4 over here. All right. Not worried about rounding that much. If you're at 35.5, all good too. So this would be your answer. This number is what the average chlorine atom weighs when you take into consideration how frequent they appear. Okay. Okay. So next we have some applications of some of the things we've learned. So we're starting with mass spectrometry. Information about isotopes is usually collected using a mass spectrometer, or a mass spec for short. So if you don't want to have to pronounce that word that I clearly can't pronounce, just call it a mass spec. A mass spec is a machine that separates isotopes of atoms by weight using a magnetic field. The separation allows us to identify the number of isotopes and their relative frequencies. It's essentially how we get this information here. Okay, so I have a machine here, kind of a slice of it to kind of see how it works. And essentially it works like this. You put a sample into this little container here. They're mowing my yard. 1 second, hold on. Okay, I think he's done mowing. So as we were saying, we have our mass spectrometer here, and we're talking a little bit about how it works. We have on the left here is where you put your sample in. So we're going to put our sample in here, and it has a heater. So it vaporizes it, just meaning turns it into a gas. So we make our sample a gas, and then we shoot electron beams at it. What the electron beams do is they just kind of knock all the electrons off of our gaseous atoms we have here. So what they turn into in this little chamber is ions, meaning they have a charge, a positive charge, and they're gases. Next to this, we have some magnets here. What we do is we accelerate these ions through these magnets. Okay, they move it through here, and then they move through a very strong magnetic field. Now, this magnetic field is what helps us separate our sample. So it has to do with how heavy these individual beams are. Okay, so now think about this. We have a mixture of heavy and light isotopes of something. We shoot them all equally into here. We shoot them through this column and into this magnetic field. And we're thinking about which ones are getting pulled more by this magnetic field. Okay, well, we have heavy and we have light things. If you're applying the same force to a heavy thing and a light thing, the heavier thing is harder to move. So our heaviest isotopes don't curve down as much in this field. Okay? And they would end up being on the far right peak down here, which if we look at this graph matches this diagram. Our far right peak is our 96 AMU zirconium. It's our heaviest isotope. It moved the least in this magnetic field. Now the lightest isotope, or conversely, should move the most. So whichever isotope is the lightest will be pulled the most by this magnet and end up all the way on the left side of my detector down here. And that actually lines up with the zirconium 90. It's lighter, therefore it gets pulled more by the magnet, and they all end up, every different isotope, depending on their mass, ends up at a different spot on the detector, and the detector detects how many isotopes land at each spot. So it just kind of keeps track of how many of them are 90, how many of them are 92, and etc. And that's how the instrument works. It's useful to us whenever we have a sample of stuff with different masses. Use the mass spectrometer, which is why it has the word mass there, okay, to separate the samples by their mass so we can see what our sample is made of. You can actually do this for elements or for compounds or really complicated things. We're going to use it for simplest application, which is this. If you have one element with a bunch of different isotopes, you can separate them using the mass spec. So this is what your data will look like, this graph on the right. These peaks represent your relative abundance, meaning what percentage of your atoms were this isotope and what percentage of them were this isotope. On the x-axis, we have the atomic mass. You might also see something m over z sometimes, the mass to charge ratio. Just know it just basically means mass. The mass here of the isotopes are on this axis. So what we can do is use the information in this graph to determine the average atomic mass of zirconium. We can make a little table where we have the mass of each isotope, and we can estimate its percent abundance using the graph. So this zirconium 90, I estimated it was just above 50, maybe like 52. Okay. I also turned that into a decimal so it would make my math easier later. Now I just repeated that with all the different isotopes, and in theory they should add up to 100% if we add up all of their different peaks. So we're going to do basically what we just did before. You multiply across, so 90 times 0.52, 91 times 0.11, multiply all 5 across, add up your answers, and you'll get your answer. So this particular sample had a mass, if you do all the math, of 91.31 AMUs, which is very close to our accepted value. Okay? So that means this sample might have been a small sample. If we got a larger sample, it probably would have been closer to that accepted value, but there is some variation, right? These are estimated abundances, and we weren't able to get exact numbers. So an explanation, just so you have it for your notes, we're going to go over. Each peak represents a different isotope. The peak occurs because lighter isotopes are moved further by the magnetic field. The higher the peak, the more abundant that isotope. Sometimes you'll have to estimate the isotope abundances because they won't be labeled. Sometimes there will be. Okay, so that is our first type of analytical tool that we use. It's called mass spec. I'm going to do a bunch of examples on your worksheet of that. All right, our next thing we need to learn about the atoms are where exactly are those electrons located. We said before they're in that cloudy area around the nucleus, but we know actually with a lot more detail exactly where they are. The electron configuration is basically a detailed list exactly where every electron is in that atom. They can have 1 electron or they can have 120 electrons, and the electron configuration just lists where everything is. Okay? Electrons are found in orbitals, okay, that are arranged in specific patterns around the nucleus. So that's the name of the space they occupy, is an orbital. Every orbital, meaning every shape, can hold 2 electrons. One spins up. The word spin up is weird. We have to go a lot more advanced to talk about it, but you can just think about it spinning one direction, and it has a plus 1/2 is a weird number we're going to get to later. And one electron just spins the opposite way. So you can think of one spinning clockwise, one spinning counterclockwise. It's essentially how it works. Okay. There are 4 different what we call sublevels where electrons can be located. Each of these sublevels have a different shape, a different electron cloud that matches. A sublevel is denoted by a letter that corresponds to a shape of a set of orbitals. You have the S sublevel, which is the one I showed you before. It's just a sphere around the nucleus. It contains 1 orbital in it. The P sublevel is a dumbbell shape, and it contains 3 orbitals. The D sublevel is a 4-leaf clover shape, and contains 5 suborbitals. The F sublevel has an 8-lobe shape and contains 7. Okay, so let's talk about real quick kind of what I mean by that. Don't need to calculate anything. So, electrons are in those electron clouds. So, the electron clouds are just these fuzzy shapes. An s orbital looks like this. Okay? It's spherical area around the nucleus, and your electrons can appear anywhere inside these. Each s orbital, each spherical shape, holds 2 electrons. So you can have up to 2 electrons in the spherical shape. You can have additional spherical shapes that kind of overlap with each other. So we can have another s orbital that'll be in this red here. And there's a good amount of overlap. So you can have overlapping atoms, but this red can also hold 2 electrons. And there's actually up to 7 for really large atoms, s orbitals. Right? And you just keep going. Each sphere can hold up to 2 electrons. Okay. Other shapes also have, we're going to do a p as well. So the p orbital, I have my nucleus in the middle. The electrons there are in a dumbbell shape like this. Cloudy area isn't actually a sphere. This is the area where a p orbital can have electrons. And there's actually 3 different places where you can hold electrons in the p orbital. And this gets a little bit more complicated, more out of the scope of the class we really need. But there's actually 3 different ways that this orbital can be oriented around the nucleus. So this one would be along like an x-axis. One would be along like a y-axis. There would actually be a third one located along the z-axis, which would be like pointing straight up and down. But we're getting very complicated. What you need to know is that P has 3 orbitals. Meaning there are 3 different places, 3 different orientations it can have electrons in. So all of this would all be considered the same p orbital. These 3 different shapes overlapping together. They'd actually have 3 names, or the px, py, and pz orbitals for the axis that they're located on. S only has 1 version, right? It only is a sphere, so no matter which way you rotate it, you don't have all these different orientations. That's why the S's only have 1 orbital, meaning you can hold 2 electrons because there's 2 per orbital. Because the P has 3 different orbitals, it can hold up to 6 electrons. 2 in each color that go there. Now I kind of see how this can be confusing because I kind of drew the same thing over here. What I drew here, each of these different colors are actually different energy levels completely. So this first black one would be called the 1s orbital. The red one here, if that would be the second one, that'd be called the 2s orbital. And the blue one is called the 3s orbital. But that's actually not the same as what's going on over here. All of these would be the same p orbital. They're all called 1p or 2p or 3p or any of those. But all 3 of these are actually just talking about, let's say, the 2p orbital. Okay. This gets a little bit confusing. Honestly, this is beyond the scope of AP Chemistry. We do talk about it in honors chemistry, ironically, but it's not something we're going to go into detail. All these different shapes, these are just the s and the p orbitals. You don't need to know for this class. But we do need to know one piece of information, and that's kind of why I drew this all out for you. S orbitals have 1 orbital. They hold 2 electrons. P's have 3 orbitals. They hold 6 electrons. That's all I need you to know. I don't need you to know their orientations or how they layer on top of each other or px, py, pz. None of that matters. All you need to know is that they hold electrons. I just wanted to give you an explanation kind of for why, so you can kind of put that together without just having to memorize it. And if we drew all the other ones, D's hold, they have 5 orbitals, 5 different versions of it. Like there'd be 5 different ways to put it around the axes. Therefore, it holds 10 electrons. And F's have 7 orbitals, which would be 14 electrons. So we're going to summarize that in a bit. But that's the main bit of information we need to know. Not confusing. So, electron configurations. Electrons will always occupy the lowest energy orbital first. So all these crazy different shapes. Electrons are always going to choose to go in order from the lowest energy versions to the highest energy. The lowest energy is actually that first sphere. The next lowest energy is actually that second sphere. And then it goes to the p orbitals. Then it goes back to the spheres. It's a really complicated order of which has the lowest to highest energy that we only figured out by doing experiments on these orbitals. Okay. They occupy the next highest energy level that they can until they get to the very, very top. The arrangement with all electrons in their lowest possible states is called the ground state. So if I have every electron in my atom, say I have 25 electrons, each of them is in the lowest state they can be in. We call that the ground state. Now, sometimes things happen to electrons. They get hit by a photon or they participate in a chemical reaction. Something happens, then they end up moving to a higher energy orbital. That's called an excited state. They get excited. Okay. Aufbau's principle here tells you the order that electrons go in. And we have this little flow chart we can follow. They always start with the 1s orbital, then go to the 2s orbital, then they go to the 2p orbital, then the 3s orbital, 3p, 4s, 3d, 4p, 5s, and it keeps following this chart. The letter tells you what shape the orbital is, if it matters to you. The number in front tells you which energy level it's on. The first, second, third, fourth, etc. energy level. But now the periodic table was constructed with this exact same information. So your periodic table can actually be broken down into orbitals as well. Okay. The S block that we have over here in purple, it also should include this helium atom over here, but helium is weird. Sometimes it's shown on the right side, sometimes it's shown over here. But you can see we can just drag it over here, pretend it existed right here. So hydrogen and helium are the 1s block. Then we have 2s. And if we just keep following an order on the periodic table, it goes to 2p, then 3s, then 3p, then 4s, then 3d, then 4p. It follows the same order as Aufbau's principle lays out. The periodic table is very intentionally constructed that way, so that the order of the elements, based on where their blocks are here, tell you the lowest to highest energy level. So the highest energy level, if we followed all of this through on this chart, would actually be right here. On your periodic table, all these elements are filled out as here as well. It would actually be this one. So you can just follow them in order by their numbers, by their atomic numbers, to figure out which order where your electrons are going to go. And we're going to use this to actually write electron configurations, and it's kind of a shortcut. We don't need to know all this other excess information we were kind of talking about. I'm going to go through several examples in just a minute. And that's what you need to know how to do. It's just understand the examples. If you don't understand these letters and numbers, especially if we didn't talk about this in Honors Chem, you'll be kind of confused, but that's okay. We can use the labeled periodic table on the previous slide to write out electron configurations quickly. So follow the atomic numbers of elements in order until you get the element you want to find. Write the orbitals you pass along the way and how many electrons or how many boxes are in each. Okay, real quick before we do it, like I said, if you were confused, that makes sense. I skipped some fundamentals that I hoped you learned in Honors Chem. We don't need to know quantum numbers for the AP exam at all. None of that will be asked on the exam, so we're not going to bother. The only reason we teach quantum numbers in Honors Chem is because it helps understand electron configurations more. All we need to know is how to write the electron configurations, which if you just kind of remember the shortcuts, is a lot easier than knowing why. Okay? With practice, I think you'll get it. But it's easier to learn with some examples for sure. So here we have 4 elements. With all 4 of them, we're going to attempt to write their electron configurations. So we're going to start with neon. So we're going to need our periodic table. We're going to find neon. Okay. Neon is up here in the top right. It's element number 10. So what we're going to do is we're going to follow through, starting at element number 1, and write down the boxes we pass through. So hydrogen and helium were both in the 1s orbital. So I'm going to write down 1s here. And we pass through both boxes, 1, 2. So we're going to write 1s2. That means there in the 1s orbital, neon has 2 electrons there. Its first 2 electrons have to go to that orbital first because it's the lowest energy one available. Neon has a total of 10 electrons because its atomic number is 10. Okay, after we go to helium, we have to keep going in order. We go down to lithium and beryllium. These are in the 2s orbital, so I'm going to write 2s on my paper. And again, there's 2 boxes, so I'm going to give it a little exponent of 2. I have 2 electrons in the 2s orbital. After that, we go to boron, carbon, nitrogen, oxygen, fluorine, neon. All 6 of these make up the 2p orbital. And for neon, it is our 6th element there. So that means its first electron would go 1, and then its next one, all the way up until it gets to neon. So it is the 6th one. So its final electron configuration, you put a 6. This is the answer. This is what neon's electron configuration is. It tells you its first 2 electrons are in the 1s orbital, its next 2 are in the 2s orbital, and it has 6 electrons in the 2p orbital. That's the answer. To go through the process again, we have a couple more. So we have sulfur next. So I'm going to use my periodic table to help me write it. Sulfur is element 16 right here. So I'm just going to follow the same process from the beginning, follow in order until I get to sulfur, just writing down all the orbitals I pass through. So it starts with 1s. I'll write down 1s, pass through 2 boxes. So it's 1s2. These 2 are 2s. There's 2 boxes. It's 2s2. Go across the table, 5 through 10 here. That's the 2p orbital, and there are 6 elements, so I write 2p6. Next row, you follow down here. 3s, there are 2 electrons, 2 boxes. Then we get over to here, and this is where sulfur is. So it's in the 3p orbital, and it's the 4th box. So we're going to call it 3p4. So I just kind of wrote that down as I was saying it. It's easier to see if you have your periodic table in front of you, but you have 1s2, 2s2, 2p6, 3s2, 3p4. And that's always its electron configuration. All of its electrons are in the lowest energy lowest energy orbital available. All right, those last 2 examples, I have chromium and I have strontium. If you feel okay about this and you want to pause the video to try these 2 real quick, that's fine. Okay, find them on the periodic table. Chromium is number 24, meaning it should have 24 electrons. Right? It's right here in the middle. So you're just going to follow from the beginning. It'd be 1s2, 2s2, 2p6, 3s2, 3p6, because you use all 6 of those this time. On to the next row would be 4s2. This next middle box is called 3d. And it's 3d, it's the 4th element. What we're going to do in class is label our periodic table so you remember that this is called 1s, 2s, 3s, 4s. This whole row is 3d, 4d, 5d, 6d. Down here are the f's. This is 4f, 5f. Right? We'll have our periodic tables labeled to help us with this. The last one I have here is strontium, number 38. It's getting really annoying to do these really large ones, but we're going to do it anyways. So we're just going to go all the way through there. I'm going to keep going in order until we get to number 38. So it should be, again, it'll start the exact same. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, we have all 10 of those this time. That next row is called 4p, we do all 6 of them. And then the last one is called 5s, and it's the second box, so it'll be a 5s2. Just like that. You'll notice they all start the same, pretty much look the same. You just stop at a different point. Okay. The noble gas configuration allows you to start the electron configuration at any noble gas instead of the beginning of the table. So simply put the prior row's noble gas in brackets and start writing the electron configuration from there. So if we go back to the periodic table, the noble gases are in purple here, this very last row on the far right. What we can do when we write our electron configuration is just start from there instead of having to start all the way at hydrogen. The configurations get really long. If you're trying to write the configuration of radium, number 88, you would have to go through all 87 other ones first. But a little shortcut we can do instead is, okay, instead of doing that, just go up one row to the very end and look at that element. That's a noble gas. Write that element in brackets. Rn, put it in brackets, like I just did here. What this means is everything up to radon like normal. So you'd have 1s2, 2s2, 2p6, all of that is included in here, all the way up till you get to radon. And then you could just start right after radon. So for this one, that would be this row down here, number 87, is 7s. And the radium is the second element, so it'd be 7s2. And that's the entire answer. You don't have to write out everything else before. This is called the noble gas configuration. You'll see this written a lot because it's way shorter. You can write the noble gas configuration for anything except for hydrogen and helium because there's no noble gas above them. So I believe I have a couple examples of this to do next. Oh, I guess not. I guess that was our example. Okay. Last thing about electron configurations. Sometimes you'll be asked to draw an orbital diagram, which is a more detailed electron configuration. In an orbital diagram, you draw a line above each of the orbitals and draw the electrons as arrows. Instead of just writing the number 2, you actually have to draw the 2 electrons, and you draw them as arrows. It's pretty much just a different format, but there's a couple of differences. So we have the same 4 elements we did up here. We're going to turn their electron configurations into orbital diagrams. So let's start with neon up here. So what you're going to do instead, it's going to be the exact same. It's going to be 1s, but instead of putting the 2, draw a line above it. For the 2s, you're going to do the same thing. Draw a line above it. And for the 2p, you're going to do the same thing, but p orbitals we learned have 3 spots to put electrons, so p's get 3 lines to put electrons on. S's get 1, p's get 3, we'll learn that d's get 5, and f's actually get 7 lines. Each of these lines is an orbital. It can hold 2 electrons, which is good because the 1s has 2 electrons. To draw an electron, you draw an arrow pointing either up or down. This is 1 electron, for example. You draw 1 pointing up, the second one always points down. We talked a little bit before about their spin in opposite directions. So this is the up spin electron, this is the down spin electron. But each line can hold 2 arrows just like that. So we're able to go on to the 2s orbital. It has 2 electrons as well, so we're going to draw 2 arrows. The first one goes up. I'm going to draw this one slightly differently. Sometimes you'll see them drawn like this, like a half arrow. That means the same thing though. The second one goes down like this. So this is 4 total electrons, just drawn slightly differently. Now, when you get to the third one here, your p orbital, you have 3 different lines. There's actually an order you put them in, because in some examples, they're not all going to be full, like this next one we'll see. But your order will always be put all the up electrons in first. So I'll do my up here, and my up here first. So I haven't put any of my down arrows yet, and that's very intentional. Electrons will prefer to spread out to all the different orbitals because they repel each other a little bit. So they'd rather not be in the same space if they could help it. So they're going to choose to spread out like this. Then when you have no other options, they're going to start to pair up. So your 4th electron would go here, your 5th one here, your 6th one here. In this case, because it's completely full, the order wouldn't have mattered that much, but sometimes it will make a difference. And that is your answer. That's your orbital diagram. It's a drawing of where all of your electrons are and which direction they're spinning and which suborbital they're in. So it has a little bit more information to it, but it's essentially the same thing. Let's look at sulfur real quick. I'm just going to go through, copy all my orbitals, 1s, 2s. Remember that the p has 3 lines. 3s, we're back to just 1 line. 3p, it's a p, so it has 3 lines. I'm going to fill in my arrows. The first ones are always going to be really easy because they're always going to be full, because you always fill up everything you can earlier first. Then you get to the p orbital, up, 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 down, down, down. The 3s orbital, up, and then down. And you always just have to pay attention basically to the last one. It only has 4 electrons. So we're only going to draw the first 4 arrows, which would look like 1, 2, 3, 4. And that's where you stop. If you drew it like this, up, down, that's wrong. This is a slightly worse arrangement because you have all these electrons paired together. They'd prefer to spread out. So in black there is my full answer for the orbital diagram. All right, so I'm going to move chromium down here where I have a little bit more room. And I'm going to copy just all the orbitals again, 1s, 2s, 2p. This gets pretty annoying to do. 3s, 3p. So I like to go through before and just kind of get it all set up. 3d, okay, D's have 5 lines, so I'm going to put 5 spaces there. Everything's always going to be full. If you have a normal ground state electron configuration, which these all are, everything will be full here. So I'm going to keep going, and I'm just going to pause before I get to my last box, because we're only going to put 4 electrons there. Put all the ups first. There you go. That's your electron configuration. Draw those a little bigger. Strontium is the last one. And again, we're just going to kind of fill in everything. S, 3D, all this is just going to be completely full. We're going to go down to the next line. Okay. Everything full. I'm even going to cheat a little bit and draw these in the wrong order because I know these are going to be full. Just to save a little time until I get to the last box. 5s. It's 5s2. Put 1, put 2. They ended up all being full. So this full thing would be my orbital diagram for strontium. All right, we have one more type of analytical tool called photoelectron spectroscopy. So it has that same word, spectrometry or spectroscopy. It means kind of the same thing. The photoelectron spectrometer, abbreviate PES, shows peaks that correspond to the electron configuration of an atom. The PES is kind of complicated how it works, but it shoots X-rays at your atoms, which knocks their electrons off. Valence electrons are easy to remove. Valence electrons are the name for the electrons furthest away from the nucleus. They have a very low binding energy. They're the furthest ones from the nucleus, meaning because they're so far away, they're not attracted to the nucleus quite as strong. Okay, we're going to learn more about Coulomb's law next week to learn about that a bit more. But just know they have a low binding energy because they're not attracted to the nucleus as strong. Now those inner electrons on the first couple of levels, non-valence electrons, are harder to remove. They have a higher binding energy because they're closer to the nucleus. The less binding energy an electron has, the further it gets flung off when it's hit by the X-ray. The lowest binding energy orbitals, the ones furthest from the nucleus, shoot further to the right on our picture. The greater the binding energy is of an electron, so those inner electrons, have less leftover kinetic energy once it's been detached, once it's been removed by the X-ray. Since most of the energy was used to remove the electron only flies a short distance, represented by being more to the left on the graph. Here's what a graph of a photoelectron spectrum looks like. You have all these different peaks. On the y-axis, you have relative number of electrons. So the height of the peak tells you how many electrons you have. This one has some little dashes here to kind of help us. This first peak has 2 electrons. This peak has 2 electrons. This peak has 6 electrons. This one has 2. This one has 6. This one has 2. If that pattern feels familiar, it's because it is. These are just the electron configurations in graphic form. The ones down here are binding energy. The ones on the left have a really high binding energy. Okay. Excuse me. Because they're really close to the nucleus, meaning this is our 1s peak. It's the closest to the nucleus, it has the highest binding energy, and it matches because it only has 2 electrons. Now our next closest is our 2s orbital. The 2s is here, 2 electrons in it, and just behind it is the 2p orbital. The 2p orbital is very similar in energy to the 2s, but the 2s is slightly above it. After a little bit, you have the 3s orbital, and then the 3p orbital, and then the 4s orbital, and you could follow your entire electron configuration in graphic form. The machine itself is complicated, but reading the graph is relatively easy. The peaks are always in the correct order for electron configurations. The height of the peak tells you how many electrons are in that orbital. The furthest to the right orbital is always the valence orbital, the one with the lowest binding energy. It's the easiest to remove. Okay, so we'll do a bunch of practice of those types of graphs, the mass spec and the photoelectron spec in class. Now our last topic for today is light. So light is a type of electromagnetic wave. So we're going to start by talking about the electromagnetic spectrum. This spectrum includes all the different types of light. When we say the word light, we're usually thinking about visible light, but light also applies to things like ultraviolet light or infrared light, or X-rays is actually a type of light. Microwaves are a type of light. So are gamma rays, TV rays. All these things are different types of light. Only some of them are things we see. That's usually what we associate with light, but all these different things are light in some way. So we have the full spectrum here. Okay, we have all the way down here are very safe and very harmless doses. Things like radio waves, cell phone towers, computer waves, the radiation from your phone, all sorts of things down here. Radios, microwaves, all these things are like lower energy waves. And the energy increases as you go to the right. Infrared radiation is kind of low energy, but then you get to visible light, it's actually pretty high. Ultraviolet's even higher than visible. You can kind of remember that because the prefix ultra means above. So this one's above visible light and energy. Infra means below. So this is below visible light and energy. That's how I remember which one of those is which. And then you get to more powerful things like X-rays. X-rays, you have to wear like a lead protective vest when you go get an X-ray because it's ionizing. It could hurt you. And even stronger than that are the rays that come from nuclear weapons or nuclear waste called gamma rays. So this entire spectrum, it kind of starts here with some safer things and goes up in frequency and goes up in energy until you get to some very dangerous things. Okay. A couple of important types. We don't talk about the spectrum a whole lot, honestly. We talk about it very, very briefly in this section. So this slide kind of has a couple things you kind of have to just remember, and it's kind of annoying. So matter can absorb or emit radiation in different regions of the spectrum, and those regions are associated with molecular motion or electronic transitions. So this is what happens to matter if these types of waves hit it. The microwave hits matter. It's associated with changes in molecular rotation levels, meaning how the molecules kind of rotate around. If infrared rays hit something, it's associated with molecular vibrational energy. So hitting something with an infrared ray kind of makes it vibrate. And lastly, ultraviolet or visible waves are associated with electronic energy levels, meaning which orbital is my electron in. We're going to talk about some of these a little bit more as we go through the year, but really not much. The last one's the only other one we're going to talk about today. Those first two, I'm going to show you some examples of questions that use this information because it is AP content, but I've never really seen it in a test question, so it's not super important. As I say, I think this is dumb. All you'll ever need to know is how they match. The word microwave matches with molecular rotations. I just think about, you put something in the microwave, it rotates around. Microwave rotation. Infrared vibration. I don't know how you want to remember that. Maybe infrared vibration. Use infrared light in medicine something, and it has the letters start with I and V. So like IV is in medicine. Infrared lights are in medicine. I don't know. Usually this will be presented in a multiple choice question. So you just have to kind of match which one goes. The last one is UV or visible light causing electronic transitions, meaning your electrons move positions. That one actually kind of matters. We'll talk about that one in a bit. Okay. Light. Let's talk about everything you need to know about light. Light travels in waves, but also particles, called photons. We call this double personality disorder particle wave duality. Ask your physics teacher if you have more questions. It's not really our wheelhouse here. We can do math using two equations to learn a bit more about light. We have the energy of a photon. A photon is an individual particle of light. It essentially has no mass, but it always travels at the speed of light, which we'll talk about in a sec. Its formula, the energy of a single photon, so a single little tiny packet of light, is equal to this constant h, which is Planck's constant, a very important number in science, times v, which isn't velocity, it looks like it should be, it's actually frequency. It's a weird little Greek v, so it's not a normal v, but it means frequency. Frequency is how many times your light cycles per second, or how many times it hits something per second. Second, here we have the speed of light formula. Speed of light is c. Okay, it's 3 times 10 to the 8th, so 3.0 times 10 to the 8th meters per second. If I didn't give you that here, I'll give it to you in class. Equals wavelength is this lambda times v. So we use these two formulas to learn about these different quantities of light. The energy of a photon is just what you would expect. It's how much energy it has. It's measured in a unit called joules, which is a capital J. The frequency of a wave is the number of waves per second. So that could be the number of waves that impact something per second, or the number of waves that pass a given point in space per second, or the amount of waves something makes per second. Its unit is hertz, Hz, or that's the exact same as 1 per second, the number of times something happens per second. Wavelength is how long your wave is, and it ranges from really, really, really tiny or to relatively large. It's measured in meters. Okay, so real quick, we're going to start this example in just a second. I just want to give you a wave. Okay, we have a wave of light here. The distance from the top to the top of a next wave is called the wavelength. Normal light, like I drew this in green pen, if this was a green light, its wavelength would be about, on the range, I don't know the exact number, but it's around 600 nanometers. So it'd be incredibly small. And when the photon is traveling through space, you can kind of think about it traveling in this wave pattern. Now for visible light, it's usually around this range. So it's traveling, if I wanted to draw it better to scale, it'd be like super, super thin waves like this. But we're just trying to see a better example. Some things, like some different radio waves and stuff, it might be more like 10 meters or something like that. So it might actually be a very long wave. So you can imagine a radio wave traveling a very long, slow kind of wave like that. The wavelength's range changes depending on which sort of light you're talking about. Now the frequency is how many waves occur, right? How many total waves do you complete per second? So if you imagine this thing was traveling, that would mean how many times does it go up and down per second? Now if the wavelength is really long, it takes a lot longer for my particle to go all the way up and all the way down. But if your wavelength's really short, you can imagine it's going to go up and down a lot faster. Wavelength is inversely proportional, meaning 1 divided by frequency. As wavelength goes up, frequency goes down. As wavelength goes down, frequency goes up. There's an inverse proportionality there. That's just kind of explaining what those words are. Now back to our example. I want to find the wavelength of a photon with an energy, E, of 1.56 times 10 to the negative 22nd joules. My formulas I have to work with here are energy gives me HV. This is the energy of a photon, which is what I was given, is equal to H. H is just a constant. It is 6.626 times 10 to the negative 34th. V, if you remember, is our frequency. The question asked me to find wavelength. That's not even close to how you spell that. I'm looking for the wavelength of this photon. So this formula doesn't by itself give me any information, which is why I have the second formula. This formula relates c, which is the speed of light, which is 3 times 10 to the 8th meters per second. Light always travels at this speed regardless of what type of light it is. So that applies to visible light or gamma radiation. It always travels at that speed. We have the same v from over here, so that's still frequency. And this weird looking thing here, this lambda, is our wavelength. So that's what we're actually solving for in this example. So that's going to be our final answer. I can't solve this equation because I know c, but I don't know v, and I don't know this. So I have two variables currently. If I'm able to find v using this equation, though, then I could plug in v and solve for wavelength. So that's exactly what I'm going to do. I'm going to plug in my energy equals h is a constant, so I know that, times v. So I'm just going to do this math. I'm going to take this, divide by this. So divide each side by 6.626 times 10 to the negative 34th. And that'll give me my velocity. Or sorry, not velocity, frequency. So my math here, I'm going to do 1.56 EE22 negative divide by 6.626 EE34 negative. I'm expecting a large answer because dividing by this negative exponent, it's bigger than this exponent. So I'm expecting a big answer, which is what I got. So I'm going to write that in scientific notation. And I'm just going to round it to 2.35 times 10 to the 6, 9, 10, 11th. That's the frequency of my wave. I figured that out using this formula. Now, take my frequency, plug it in here. So I know my speed of light is 3 times 10 to the 8th equals wavelength times the frequency I just solved for. Get lambda by itself by dividing both sides by this. So I'm just going to do 3 times 10 to the 8th divide by 2.35 times 10 to the 11th. Round to my first 3 non-zero digits, and the unit for wavelength is meters. So this wave has a wavelength of 0.00128 meters. So it's quite small. All right, almost done here. Last little topic is electronic transitions. Atoms and molecules can absorb or release photons of ultraviolet and visible light. As we learned before, ultraviolet and visible waves relate to electronic transitions. Electronic transitions means that electrons move from one energy level to another. We can calculate the exact type of photon needed to move an electron from one level to another. The electrons of an atom can get excited when they absorb energy. Excited means the electrons go up to a higher energy level than they were supposed to be in, meaning maybe it was in the 2p orbital normally. If it absorbs a photon, it can go up to the 3p orbital or the 4d orbital or any other orbital above it. For electrons to return back to the ground state, they need to release energy. They release this energy as a photon. The photon will appear different colors or ultraviolet as it corresponds to the amount of energy lost. Okay, so here's kind of my example I have for you here. Can't quite see the bottom, but this says energy absorbed down here and energy emitted down here. So this represents all my different energy levels where my electrons can be. Energy level 2, like the 2s orbital, for example. Energy level 3, like the 3s orbital, or the 4s orbital, or the 5s or 6s, all the way up. Now, to make an electron go from the energy level 2 to the energy level 6 or any other energy level, you must absorb a specific photon of light. A piece of light, a tiny little photon with the exact right wavelength, would have to hit this electron, and that extra energy it receives would be just the right energy to go up to this top level. Now, it has to be a very specific wavelength because this electron can never exist in between these energy levels. It's a quantum value, meaning it only exists at discrete energy levels. You can never have an electron at the 2.5 state or the 3.1 state or the 5.0001 state. It has to be exactly on these levels. That's kind of one of the things we skipped over when we didn't talk about all the quantum mechanics stuff, but we should know that electrons have to be on one of these lines. And you see that with all of these examples. Okay. In addition, one little sidebar to that means when this electron absorbs this photon, it doesn't travel up to the 6th energy level. It just appears there. It is just now in the 6th energy level, kind of like magic. Quantum stuff is really weird. Okay. And this is one of the main examples of that. So if this absorbed this photon, just the very next instant in time, there's no travel time, it would just appear at the 6th energy level. Now, over here, we have energy level going down. To go down an energy level, this electron is going to release release a photon, right? It has to release a photon, and depending on the exact amount of energy difference between these, that photon will be different colors. We learned a little bit ago that these different photons would all have different energies, and these energies correspond to how far the energy drop is. You notice the highest energy drop from level 6 to level 2 is purple light. Purple light actually has more energy than red light or any of the other colors of light. Red light is actually the weakest color of light, and that's why this drop from 3 to 2 has a piece of red light. You're not dropping as far, you're not losing as much energy, and therefore you can use a lower energy photon to emit to do that. Okay. It looks a little backwards when you look over here, though, at the wavelengths. The number 410 is the lowest number here. Why is it the strongest photon? And it's because wavelength doesn't affect how strong a photon is. It doesn't affect its energy. We just learned that frequency does, according to our formula. Frequency goes up, energy goes up. Okay, well, how do you make frequency go up? We just learned that it's inversely related to wavelength. To make frequency go up, wavelength has to go down. So the lower wavelength something has, the more frequency it has, and the stronger it is, therefore. So a strong wave, back to here, if I wanted to compare these two, this wave has a lot higher energy than this wave. Because this one has a higher frequency, therefore it has a higher energy. This one has a much lower frequency, therefore it has a much lower energy. So there's all sorts of math you can actually do to calculate this exact number. We don't have to worry about that. What I want you to know, for an electron to go up, it needs to gain a photon, and it needs to gain a photon of a specific wavelength. That wavelength depends on how far the transition is and what element you're dealing with. When you lose energy, meaning something's cooling off or something, and you go down, you're going to emit colors of different light. Okay? This is why sometimes when you heat up a metal, it produces all these different colors. It's actually this transition you're seeing. The electrons being excited by the heat, okay, absorbing those photons, and then when the electron wants to go back down to ground level, it's emitting photons of that color. So something that has this transition would appear purple, or this one would appear blue. And different elements and different compounds have different complicated transition patterns. This is hydrogens actually, so if you're able to make this emission occur with hydrogen, these are the different colors you would expect to see. Okay, the important things to remember are photons are emitted or lost when dropping energy levels. The color of the photon emitted is the result of the amount of energy lost from the drop in energy levels. Red photons are lowest energy, purple are the highest. Remember that high wavelength is actually a low energy. Think about those math formulas and how they relate to each other. Conversely, atoms can absorb photons of specific wavelengths to push electrons, I should say, to excited states. I guess either way it works. The photon needs to have the exact right wavelength to make the transition happen. Photons are absorbed to move up energy levels. Electrons can never be in between energy levels, only exactly at them. Okay, that's actually our last slide here. A lot of information, a lot of different math terms, kind of a grab bag of a whole bunch of different topics. In class, we're going to go over, practice a whole bunch of these, do a little bit of the math with the light and stuff at the end. Hopefully the first half of it was easy and maybe it got more complicated as we went, but that's it for today. So thank you for watching and I'll see you later.